Before going to the presentation, I would like to say thanks to Santosh sir that he has accepted my this to have a presentation in my FDP sir. Uh, Before moving towards forward, I would like to say that sir is having a vast experience in the Velisite technology field, and sir is having lots of papers and in SCI journals, even transactions also in Velisite. Uh, Sir is going to give the his presentations on the nano, how the electronics field is going towards the nano and it is working in nano field. So I would like to request, in this case, I would like to request my colleague Dr. Jiten Shukla to please give a brief view of Professor Santosh sir. Please, Jitendra, please.
Thank you, sir. An ignited mind is the most powerful weapon on the earth, and this is got through the education. With these words, uh, a very good afternoon to all the dignitaries and dear participants. On behalf of Electronics Engineering Department of IERT Prayagraj, I, Jitan Kumar Shukla, welcome you all in the third session of third day in the Faculty Development Program organized by the Department of Electronics Engineering, IERT Prayagraj, sponsored by the AICT Training and Learning ATAL Academy, New Delhi. With great pride and honor, I am here to introduce to you the speaker of this session, Dr. Santosh Kumar Gupta, sir, Associate Professor in the Department of Electronics and Communication Engineering, Motilal Nehru National Institute of Technology, Prayagraj. Professor Santosh Kumar Gupta, sir, completed his postgraduate from IIT Bombay and doctoral degree from NIT Silchar, Assam, India. His area of research is modeling of semiconductor devices such as MOSFET, TFETs, FinFETs, MODFETs, and digital VLSI design, analog VLSI design, and VLSI signal processing. He is a member of IEEE and IEI Fellow. He chaired two international conferences uh, such as IEEE 2020 and Springer International Conference on Micro Nano Electronic Devices Circuits Systems in 2021, organized by the NIT Silchar. Professor Santosh Kumar Gupta sir received honorary Rosalind member of London Journals Press on May 2021. Professor Santosh Gupta sir completed two projects as a principal investigator. One of them was on a special manpower development program, second SMDP second, in the area of BLSI design and related softwares, sponsored by the DIT MCIT Government of India in June 2012, and another on analysis of various structures of MTJs for possible applications in MRAMs and logic circuits, sponsored by CSIR SRF in 2021. There is one ongoing project where Professor Santosh Gupta sir is co-principal investigator on Special Manpower Development Program Chip to System Design, funded by MITI, Government of India, at MNNIT Prayagraj. He is also reviewer of IEEE Transaction of Electronic Devices, IEEE Access, International Journal of Taylor and Francis, Silicon Springer, Super Lattices and Microstructures elsewhere, and many more reputed journals. He organized several workshops, short-term courses, expert lectures at MNIT Prayagraj. He has also given many expert lectures at different prestigious institutes. Now, I request and welcome Professor Santosh Kumar Gupta, sir, to come and enlighten us. Welcome, sir.
Okay, thank you. Thank you, Dr. Jiten Kumar Shukla, for this very big introduction.
Welcome, sir.
Before starting, let me congratulate all the IERT organizing committee members of this ATAL FDP on recent trends of emerging research, advances in design aspects and innovative modeling techniques with miniaturization of electronics devices and circuits.
Thank you, sir.
So uh, I also thank your director, Dr. Bimal Mishra, for uh, giving us opportunity to uh, come here and share our thoughts. Special thanks goes to Dr. Yatin Gaurav, who has been in touch, okay, all the time. Yeah, so thank you, Dr. Yatindra. I also thank the organizing committee, Dr. Vivek Kumar Barnwal, Dr. Jitendra Kumar Shukla, Dr. Alka Verma, Dr. Nimish Kumar Srivastava, Mr. Puspendra Kumar Gupta, and Dr. Rohit Gupta. Okay, so let me start before my presentation. First, let me share my screen. I think screen is visible, okay. Huh?
Yes, sir.
Okay, so as introduced already, the talk is about nanotechnology issues and technology trends. So we will try to focus here what are the recent trends in nanoelectronics. So we will start with a very basic, say, MOS transistor and see what are the challenges and what are the possible solutions for these challenges in nanoelectronics by suggesting different solutions for the same. So let us first get interested in this semiconductor technology. So first thing is driving force is say market, of course. So total semiconductors market in 2017 was $335 billion. Out of this, integrated circuit actually contributes to $274 billion, and then there are some discrete sensors and up to components that contribute to the $60 billion. So the old data is here. In integrated circuits, we can see almost $229 billion is shared by digital designs and $45 billion are shared by analog designs. Out of these, we can see $229, almost all the digital designs, that is done using the MOS transistors. In the MOS transistors, actually using this MOS, within the digital design, we have memory, we have uh, microprocessors, logics. Inside this, we have in the memory, again, we have DRAM, flash, microprocessors, microcontrollers, special purpose logic designs, standard logic. So all these things we can see that a large share is governed by the MOS transistor. So this is actually very important for us to understand this MOS transistor. Again, this is giving semiconductor sales revenue worldwide from say, 1987 to 2019. So year by year, we can see almost exponential growth kind of thing. This is almost a kind of exponential growth which we can see here in this semiconductor sales worldwide. So this is one can say very emerging field. So looking at these aspects, that market share of the MOS transistor is too large, and mostly the digital design is governed by the MOS transistors. Also, we will see that analog design is also, most of the analog designs are also done by the MOS transistors. So what is expected here? Day by day, we see complexity of the logic is going to increase, typically infinity. Delay of the different logics, okay, when we implement different circuits, it is expected to come zero. Okay, so that means high speed. We should have the high speed. Power is another issue. We want very low power devices, very low power circuits, and typically we want that our circuit should not consume any power. It should go down to zero, but it is not going to happen. But these are the things which are expected. Cost. We want that our designs, our circuits should be very cheap, so that we can have more benefits out of it. Okay, so cost should reduce to zero. Another very important aspect is design time in our circuits. Here we see that a lot of time is going to actually consumed in designing our a circuit. Okay, we design, test, and then market it. By the time the technology is going to change, we have seen from our previous experience in last few decades that a technology is giving matured by the time and the technology is coming into. And also we see so many applications coming okay in very less time. So design time is also a very crucial thing, and we want typically that design time should come down to zero. Means we should be able to design the circuits in within no time. And another thing is size of the circuits. Okay, they should also come down to zero, means they should consume as less area as possible, so that we can put more and more logic in the given area on the silicon. So looking at uh, these are the things which are expected in the coming days. There are different areas of micro and nanotronics we can see beside design, beside CAD tools, technology and fabrication, material science, physics, modeling and simulation, characterization, testing. Okay, so these are different areas in which we can work and do many more things to achieve these expected goals. As already narrated that we have lot of application of the MOS transistors, mostly in digital and analog electronics. So different circuits we implement using these MOS transistors, like inverters we can implement, amplifiers we can implement, some impedance transformation circuits. Okay, so they are not limited to these only circuits. There are almost all the digital designs are done using the MOS transistors. So let us have a brief introduction of this MOS transistor here. The MOS transistor, the heart of the MOS transistor is something called as MOS capacitor. So a typical MOS capacitor is shown over here. In if we look at this expansion of this MOS, then M stands for metal, O stands for oxide, and S stands for semiconductor. So metal is not a generally it could be metal or some very conductive material like polysilicon, hablet or polysilicon are also there that can work as a metal. Then oxide is typically silicon dioxide, but it could be high-grade electric materials also. And semiconductor is here for a silicon, or it can also be some other semiconductor materials like silicon germanium, silicon carbide. So we apply some voltage on the top metal side, that is sometimes called as gate, and there is, depending on the voltage applied, we may deplete or accumulate or even invert the uh, semiconductor in its nature. That is p-type. It is p-type semiconductor. So we can make it n-type, or we can deplete it of charge carriers, or we can accumulate under this. That is p-type charge carriers we can accumulate.
पढ़ाने में लगा हुआ है.
You people should not
So,
attend. तुमको करना ही नहीं चाहिए.
so
Nobody can ask you any question कि तुमने क्यों नहीं join
सर
किया.
नहीं चिकन
excuse me, please be muted.
साउ क्या लिखा है सर ने? मैं कहता which movie recently watched? Check on YouTube.
Pooja Sani ma'am,
नहीं, नहीं,
please mute
Check.
your mic.
So this mass canister actually is used
बंदे को पूछ
here.
लेना होगा, क्योंकि मेरे को activation
If we
करनी है,
use
आज
source
बंदा
and
उधर
drain
आपको
with this, then it forms the basic mass structure here.
आपने ना कुछ भी कराने करा लो.
We can apply different types of voltages here on
फिर भी मैंने अपने पिछली को बोला बंदे activation कर
at the
दिया.
drain and gate of this transistor to make it operate in different region of operations. So we can have it to be operated in the linear region of operation. We can make it to operate in the saturation region of operation if these conditions are being fulfilled here. So we have also we can characterize these transistors using very basic equations in the linear region of operation and in this saturation region of operation. So we have here very means general mass transistor output characteristics here, showing the different regions of operation like linear region, saturation region, and there is something called as breakdown region when we exceed the applied voltages at terminals more than the desired one. So here, if there is something called as threshold voltage, if we apply a voltage less than threshold voltage, then the current flow is limited by something called as diffusion. Whereas if we apply a voltage greater than that, and then it is and apply we also apply a VDS drain to source voltage, then it actually conducts according to the drift current. So and in this diffusion, when we have the diffusion current, the current actually changes exponentially with applied voltages. The fundamental limit in the MOS transistor, if we look at, is something called as subthreshold swing. So subthreshold swing is the required voltage to make or to reduce the drain current by a decade. So fundamental limit in this MOS transistor is 60 millivolt per decade. So at least we need to apply a voltage equal to 60 millivolt to reduce the drain current by a decade. So that is the fundamental limit of the MOS transistor. This is very important for the switching purpose of the transistors. So to make a logic faster, we have to reduce it. But MOS transistors are not able to cater this particular limit here. Okay. So and there are some more things here. As we have seen in the our desired goal, that we need to have more and more transistor packed in a given silicon area. Okay, so for that reason, we want to reduce the size. That is one temptation, and this is done by using scaling. So there are different types of scaling which are there. And mostly here, if we reduce the width and length of the transistor by 0.7 times, then almost we are able to reduce the area by half. Okay, so that has been done, and it was predicted in early 1965 by Gordon Murray, and he also said that this kind of trend can prevail for next 10 years in 1965, and if every 10 years after that people have been sitting down and then looking at the then present technology, see whether this is possible or not, and how one can do without changing much of the um, transistor characteristics. So using this, we have been able to reduce the size of the transistors drastically, but the scaling doesn't come without cost here. When we reduce the size, there are some secondary effects also which come into picture. So, so far technology has scaled well, but will it in the future will also be able to scale down the transistor size here? So natural answer comes here that we have to stop somewhere, and now the time has almost come, and that there is no more possibility of scaling. So here actually we have a tabular comparison here that in this early 80s and then in 2000 what the technology have been there and what in 2000 we have and what we will be having in future, say in 2020. So in if we see here, then gate oxide was 40 nanometer, then in 2000 it is 2 nanometers, so we can see 20 times reduction in gate oxide. Similarly, polysilicon almost 20 times reduction. Metal layers, to contact different regions, we need to have different metal layers actually for connecting gates and drains, sources, all these things. So this has increased to from 1 to 6 and now 10 metal layers or more than that. Density of SRAM has also increased from 4K to 16 million and now 256, almost 4,000 times increase. Cell area that has also increased almost 200 times, and access time has also so increased almost 40 times. So recently we have this Intel Core i9 processors, and based on this Ice Lake, which uses 7 nanometer lithography, and it is out almost. These are some pictures which shows trend in the transistor count year-wise from early 70s to 2010. The trend has been increasing, that the transistor count is steadily increasing year-wise. If we look at the microprocessor frequency trend, then that is also increasing. But nowadays, what is happening is that the frequency is not, people are not able to increase the frequency, but people do increase the number of cores, number of threads in a processor. This gives a glimpse of transistor density comparison. Density of the transistor is also increasing steadily, and this is possible due to the scaling here on the technology node. So minimum feature size has also increased, decreased starting from 70s to 22. This is giving us a picture. This is almost steadily decreasing. So nowadays, actually, different processes exist which can manufacture as small as almost 5 nanometer, and even now we can see 3 nanometer transistor sizes. Okay, so pioneer is TSMC, Taiwan Semiconductors, and that is followed by Intel and Samsung. So these are three major manufacturers worldwide, TSMC, Intel, and Samsung, who are pioneering now in scaling down this transistor. Others are there also, like global foundries, you can see here, but they are now not much interested is in these lower technologies because of the cost involved into it. So this downsizing of the transistor has increased drastically the density of the transistors. So transistor integration capacity is now increasing, and we are moving towards the 1 billion capacity here. So let us look at what are the challenges which comes into picture when we do the CMOS scaling. So CMOS is nothing but it is the combination of PMOS and NMOS together, and both are having the similar characteristics. Okay, so a typical MOS transistor is given over here, and the different things are shown over here. Like first thing we can see, due to scaling, the threshold voltage is not decreasing that much actually. So BDD minus BT actually decreases because due to scaling, BDD is scaled down, so BDD minus BT decreases the overdrive voltage that we call as. KT/Q successor slope is not that much scaling. Gate tunneling is increasing. Inversion layer charge, okay, that also is going to be hampered by scaling here. There is something called as polysilicon gate depletion that also comes into play. Due to scaling, there are different tunneling regions created, like between drain to body, source to drain, and due to scaling again shortening of the device size, we have high electric fields, and because of that, we see mobility degradation and also reliability issues. There are also dopant related, okay, dopant profile related problems also, which induce when we scale down the size of a transistor, like transient enhanced diffusion is there, ion implantation problems, RTA problems are there, the discrete random dopant fluctuations that also play a role. Okay, so there are several challenges associated with this scaling. Another thing, let us look at the verdict here, that is transistor a good switch. We are using the transistor for switching purposes for designing the digital circuit. So if we see this, then transistor is no more a good switch when we scale down its size. So when ideally the gate current should be 0 here, like I0 I is equal to 0. When it is off, okay, when it is on or off, gate current should be 0, and there should be no the channel current when the switch is off. But none of these are fulfilled here when we have the scaled transistors acting like a switch. So gate current is not 0, there is subthreshold leakage also. So there are different things which come into picture. We have a very big problem also. Drain is coming nearer to the source due to scaling, and we have a severe problem called as drain induced barrier lowering. So drain actually is going to control the channel charges more, and also interact with the barrier between the source and channel. and so threshold voltage decreases, and a current may we can see an increase in current due to this DIVL. Another problem is when due to scaling is channel length modulation. In the large transistors, this was not a problem, but when we shorten this transistor size, then this is a problem. So effective channel length is going to decrease, and hence we may have some secondary effects like ballistic transport may play a role into this. So these are some of the problems here which may come due to the scaling of the transistor. So also some other short channel effects like threshold roll off may also come into picture. That is, instead of increasing the threshold voltage, it starts rolling off. We can see some secondary effects due to this gate oxide in the term of the non-zero gate current. So this also impacts on the drive current. This also impacts on the circuit performance and arises the reliability issues. Some more effects like hot carrier effects also come into picture because of the increased electric field, and due to the shortening of the transistor sizes, we see that some high energetic carriers may collide with atoms and impart the energy to that, and thereby actually generate the secondary effects, and that is a hard carrier, that is also called as hard carrier effect. Okay, so this also degrades the performance of the transistors when they are operated at for prolonged times here. So statistical dopant fluctuations, that is when we have the large size transistors, we don't have such problems. But when the transistor is of a small size, even the placement of dopants uh, that we can count actually, and that can drastically change the characteristics of the transistors. So that we call as dopant fluctuation here. Okay, so this has also this may locally change the threshold voltages or other characteristics of the transistors, and that has to be controlled pretty good. So for all these such things here, we need good technology here to control all these. Another problem we have see, that is subthreshold leakage. Subthreshold leakage is not only dependent on the scaling, but it also is dependent on the temperature. And as you can see that if the temperature increases, then this subthreshold leakage also increases because of the increase in temperature. So temperature gives energy kT by Q to the carriers, and that increases the this subthreshold leakage. So also we see an increase in the leakage power due to this scaling down of the transistor sizes. So leakage power has steadily increased, as we can see, very large at 45 nanometer technology, up to 45 nanometer. The gate leakage power, that is also now not negligible here, but that also counts here. So that is also increasing. So as The oxide thickness is scaled down. BDD is also scaled down. BDD has also to scale down, and if BDD is scaled down, then we have lesser overdrive voltage, and that slows down the circuit. Okay, so these are the different associated problems with these technology scaling. And leakage power has increased almost exponentially. Now we are going into something called as power crisis regime because of this technology scaling, because of the different the leakage powers are increasing, and also we can see that the circuits are becoming slower here. Indeed, initially when we were having the scaling down of transistor, we were having the speed up of the transistors, but now because of these secondary effects, these are not happening. An extrapolated curve we can see over here, which shows how severe the problem is going to be, like power per unit area in centimeter square of the chip, how much power is being dissipated is increasing nowadays almost exponentially. So here we can see that we have some restrictions that what should be the order of the of current for different applications. So this is a big issue for the handheld devices like and also DRAM. That is, it is almost 100 picoampere per micrometer. So I of is really very small, desired, whereas for desktop computers it is relaxed a little bit. So we also see some circuit and device interactions happening, which also impacts the performance of the circuits. So some of the circuit parts which we need to perform very fast, we can have higher BDD for that, and those circuits which are not that much important, we can have the lower BDDs and lower threshold voltage for those. So here the concept of dual BT and DT mask comes into picture for such a devices for such a circuit topology. So let us look at some of the possible solutions for these problems. We have discussed so many problems arising of the scaling. Now let us look at the solutions of these. So it shows here that how the technology has reduced from 50 nanometer to say 35 nanometer, and showing this AMD technology development. So starting from the bulk transistor to double gate, then FDSOI, fully depleted SOI, then strand silicon. So it is not only reducing the size of a transistor, but something additional has also to be done in order to have the adequate efficiency of the transistors. So different material engineering has been done, different gate engineering has been done to achieve the goals. So we have possible solutions on technology front, like either we can do some changes in the processes, or we can also play with the materials. So FEOL or BOL processes we can target to design such that it gives a better performance. Also, we can look at the device structures. We can also explore some novel device operations. A typical FEOL process is given over here, and we can actually do some innovation in any of these processes and have a better uh, control of the device performance. Okay, so right from these wafer preparation, then grow oxide, apply photoresist, then be align masks here, exposure, then development is not shown over here. I think the some undesired regions, keeping the desired regions, doing some implants and our other our diffusion. Okay, so these are the front in the offline okay processes, fuel processes. These are mostly the high temperature processes. So we can do some innovation in this. There are BOL processes also after we are having say uh, transistor built up. Then for connecting different regions, we put some holes, connect the holes through metals layers with different regions. These are low temperature processes. So these here also we can do many more things so that uh, by using the better materials like mostly for connecting here the low resistance materials may be used and to reduce the parasitic capacitors we can also increase the separation between these different metal layers. So all those things can be done here. Sometimes also low K materials can also be filled in between to reduce the parasitics so that we can speed up the transistors. Okay, so these are things one can do in BOL. So FUL and BOL are these at the device level when we are actually doing the when we are fabricating the device. At that time, we can do either of these things. So we can use novel processes or novel materials to achieve the goals. So we can use high K gate dielectrics, we can use metal gates, we can use work function engineering, we can use ultra shallow source drain junction formations, silicide technology one can use self-aligned silicides, some elevated or raised resource drain can also be done, can be used, but elevated raised source they increase the parasitic substances uh, and may not be of good characteristics. So one can do textile growth also of these regions. Sometimes these source and drain regions, instead of elevated, it is grouped inside the uh, the body of this transistor. Okay, so that can also be done. Low K dielectrics can be used. Metal barriers and capping layers can be used also. These are some novel materials which we can use. Gate leakage, if we see, then it has actually as we reduce the technology nodes here, then the effective gate oxide, okay, and on the vertical axis it is effective gate oxide, effective gate oxide is decreasing. So that is steadily increasing the gate leakage because gate and channel they are coming closer to each other. So one can use different things here like uh, to increase the effective oxide thickness and reduce the gate leakage. So one can use metal nitride silicon, something called as MNS, down to 100 nanometers in length. And this was reported by reported in Bilkai Technology Symposium in Kyoto. So also we can use this high gate in the gate to increase the effective oxide to reduce the effective oxide thickness, so that the gate control is, we are not losing the gate control, but we are able to put the gate away from the channel, so that the leakage current is going to decrease. So different processes has been actually explored here. But using the high gate transistors, there is something called as fringing field effects come into picture, because the if the physical thickness of the oxide under the gate, that increases, even though the uh, effective oxide thickness is reduced, but the physical thickness is not is small. Okay, so that increases the fringing field effects, and so reducing the gate control over the channel. So we need to apply a more gate voltage in that case, uh, for this to have the same controllability on the channel. There is an issue called as boron penetration issues in polysilicon gates. So uh, polysilicon gates may be avoided; they can be replaced by the metal gates. Polysilicon has been traditionally used because of its cheaper, uh, and because that is cheaper and also compatible with the silicon. Okay, that has good, you can say, interface with the silicon. Ultimately, the polysilicon is made of silicon, which is heavily doped. So this boron penetration may be problem when we are actually doping the p-type implant in the channel. So that some of the boron may also be get penetrated into the polysilicon gate. So that may create a problem here. Okay? So that's the problem. So metal gates are being used now widely in place of the polysilicon. There is one more issue like polysilicon depletion. When we apply some gate voltage, then the polysilicon, because that is ultimately heavily doped silicon, that gets depleted. So effective oxide thickness increases there. So that in that way that loses a little control over the channel. So these are very minor things, okay, but these do have impact when we have millions of transistors in a circuit here. Okay, so these have some impact, some noticeable effect, impact actually. So it is advisable now to have the metal gates, and widely people have been investigating different compatible metals which can be used as gate material. So TIN gates along with TiO2 gate dielectrics, these kind of things have been explored. Silicon germanium gate has also been used sometimes for reducing the polysilicon depletion problem. So advanced gate electrodes can also be used in. We have traditionally used a single gate. We can also have a dual material gate, we having two work functions, one at the source side and at a different work function material at the drain side to better control. But these are going to have, one has to satisfy some of these conditions, that these should be stable, these there should not be metal diffusion, and It should be integratable. So such a material has to be investigated and maybe used for replacement. So dual metal gates can be used here of having different work functions with different IK materials underneath. Sometimes to have a better interface with the underlying silicon, people use silicon dioxide and high K dielectric in the stack. So a high K stack may be used in place of just using these either high K dielectric material over there. So these are some of the trends which are being used to have a better behavior of the transistors. We can also use mid-gap gate materials. Apart from these, the previous thing was concentrated on the gate side. Okay, so what are the pros and cons of using the polysilicon material, and what are the replacements for those? Now we can also do some type of engineering on the source and drain side to have a better control over the charge and effects. So a typical mass transfer is shown over here, and we can see that there is some source drain engineering is done on the source side and drain side. Ultimately, the transistors are placed on a opposite type of material substrate like P substrate we use for n plus source and n plus drain here. So there is essentially a PN junction kind of thing is going to form at source drain, source and substrate and drain and substrate. So we have PN junctions. So if we apply some voltage on the drain, then these depletion regions are going to increase and make actually capture a part of the channel. So that's how the effective channel length also starts decreasing. So we can actually do to avoid this problem of depletion region at these PN junctions. We can do uh, a little higher doping uh, on the side of the channel where we have the interface of the source and drain with the channel. So in that region we can do that kind of thing. Okay, so sometimes these kind of things are called as pockets. We can do some kind of pocket formations. uh, we can also have ultra shallow source drain junction formations to avoid these some of the short-term effects. So for doing this ultra shallow source drain junction formation, we can heat the sample beyond the melting point of silicon for a short period of time in the order of nanoseconds. And this significantly enhances the solubility without appreciable diffusion of these materials here to form these junctions over here. The different process steps are shown over here, but because of the time constraint, we will not be able to discuss all these here. Plasma immersion and implantation can also be done to make the ultra shallow doping profiles, and ultra shallow doping profiles at the source and drain is required for enhanced structural effects. So, but plasma implantation may induce some damage here, like charging damage can also be formed here, which may fluctuate the device characteristics from the desired one. And charging damage is dangerous because it is cumulative in nature. It keeps on accumulating. So the effect is destructive in nature. So that's why it may be avoided here or may be done with caution here. Silicides are also sometimes used. So elevated raise source drains can also be used here for source drain. So a P-FET and N-FET uh, SCM is shown over here, having the elevated raised source drain along with their characteristics here. So in 2001, actually this is a little older slide here. So in 2001, AMD reported what's smallest transistor having the gate length of 15 nanometer, which were at 0.8 volt and have the ion and I of currents 615 microampere per micrometer and 500 nanoampere per micrometer respectively. So these uses as a nitride and oxynitride stack as gate electric with effective oxide thickness at as small as 0.8 nanometer or 8 angstrom here. So some metallization schemes can also be used in ultra large scale integration here for in BOL for so here just we are looking at now this BOL that is backend. So in the backend mostly we are doing the different connections here. So say gate, drain, and source. These are connected by different regions. So different metallization schemes are used here, like tungsten are being used for initial contact here. Then later one can choose the copper or aluminum. So these mostly are uh, forming of the something called as holes or vias and then depositing some metals here. So different metal layers we can see here 1, 2, 3, 4, 5, 6, 7. These kind of metal layers these are being used here for connecting here different regions. So these interconnects limit the performance and to enhance the performance, low resistance interconnects are being preferred along with low K for isolations. So different regions we can see here how they are being connected. They to the source near to the source are drain and gate. These are uh, connected with titanium silicide. Later by this second stage is connected by tungsten, then aluminum, three stages here, and later this copper here. So these kind of interconnects are being used. So different processes we can use to do these interconnections here. Like we can use dual damascene process here to achieve the goals over here. So different things are shown over here that we have low K dielectrics, then in between we have the metals for interconnections. So, interconnect technology requirements has been also been demanding, but that has not been catered uh, as it was demanded, like number of metal layers increasing. So number of metal layers increase means the process complexity is increasing actually, and barrier thickness is decreasing here. So the figures in red zone, these are actually the alarming situations here, that there is no more possibility beyond this, and there is no options also available to substitute for these, and these needs more attention here to cope with the problem coming ahead. So copper has been traditionally used, but copper is a fast diffuser, and that's why one has to go for newer materials which have better performance, better quality. So as we have seen that to reduce the parasitic effects in the interconnects, we need to reduce the resistance, as well as we need to reduce the capacity effect. So in the interconnects here, as we can see that there are two or more wires which may run parallel, and in between these we may have the dielectric material filled with. So these gives like a capacity effect here. So this capacity effect has to be reduced here, and for that we need to have the low K. So low K porous silica films have been used for this purpose, and a typical this flow of process flow, okay, that is given over here. That by using these, one can achieve this. Uh, One can have the low K porous silica films. Metal barriers and cave films are also required to reduce the diffusion of contaminants, and these are also equally important. So different metal barrier tapings like tantalum can be used here for the purpose. So we have just seen here the some of the fuel and fuel processes which can be used to have a better transistor. Now let us look a little bit about the noble structures, which we can also have a- apart from the processing. So that processing step actually is mainly from the manufacturing point of view. But structure is something like that we are adding some special regions for some special purposes into the existing mass transistor structure. So like we can have single halo or double halo MOSFETs. In the single halo, we have a pocket made on the drain side or source side. In the double halo, we have the pockets to be placed on the source and drain both sides. Okay, so that can effectively reduce the short channel effects. We can also have dynamic threshold MOSFETs in which the threshold voltage can be modulated or being controlled by just changing the voltage on some terminal. So body is the most advantageous terminal which is not being used in a MOSFET working, but we can tune the MOS transistor threshold voltage by applying some suitable voltage on the substrate on the body of the transistor. Okay, so there are basically two types of voltages which one can apply on the body. One is forward biasing voltage kind of thing, and one is reverse bias voltage. So if one increases, if one applies a forward biasing voltage on the substrate, then threshold voltage will reduce actually, and one can increase the current because the overdrive voltage will increase and that will increase the current, but that is also going to increase the leakage current. So one will have this disadvantage when forward biasing the substrate. One can also reverse bias the substrate. If one reverse biases that substrate, then threshold voltage will increase and the current will decrease. So these things one can do. One can dynamically actually program. One can say the threshold voltage. Nowadays, actually, the trend has been like electrically induced junction MOSFET. So electrically induced means we don't dope, okay, the source or say drain or but we apply some suitable gate, some suitable uh, metal on the source side and drain side with suitable work function so that it induces the charge plasma kind of thing, and that is called as electrically induced junctions, and these has been found to give a better uh, characteristics. Double gate and gate all around structures. Okay, different structures can also be used. We have seen so many things so far that in the transistor, instead of using say single gate, we can use double gate. We can use gate all around structure. The recently transistor being fabricated by TSMC, that is of 3 nanometer size. This is basically gate all around structure. So they are using gate all around structure for this. So in the short channel, the highly skilled devices, these innovative novel structures are going to be advantageous. We can also use silicon on insulator or silicon on nothing structures kind of thing. Silicon on insulator is that in which we are going to put our active region of the silicon on, not on the bulk silicon, but on the thick silicon dioxide or some other oxides. So that is also going to give a better performance because we are removing or we are not controlling the full body but only like the active region of the device. So in that way it is going to, initially when people started with SOI, not aware of that of what the sizes what the thickness of the silicon could be chosen. So people were having problems with these also SOI technology, like partially depleted SOI or fully depleted SOI were having over there. Okay, in the partially depleted SOI that was having a problem called as kink effect. So in the kink effect, suddenly some current was increased. Okay, there was some current, and after that there was sudden increase in the current. So in the partially depleted SOI. So nowadays, it is preferred to use the fully depleted SOI, okay, in place of PD. There are some other innovative novel structures like vertical MOSFETs and strained silicon channels. In the strained silicon channels, we can use silicon germanium or some other materials which induces strain, and strain actually is going to increase the mobility of the charge carriers and increase the current. Okay, so such type of uh, structures are being uh, explored here. Germanium is having a very large mobility, of course, as compared to the silicon. So germanium transistors are also reinvented actually. So if we want to, for a given off current, if we want to increase the on current, then one can go for the strained silicon channels or germanium transistors. So these are different options here which one can play with. So in the new device structures, there are some source of improvement like charge density we can improve, but the successor slope and equivalent charge is going to be affected here, and the method using which we can achieve these are double gate FETs, or we can also lower the operating temperature. We can also achieve a better carrier transport. In the to achieve the better carrier transport, one can target the mobility, the carrier velocity, the ballistic transport, and these can be achieved by strained silicon or high mobility and saturation velocity materials like germanium, indium gallium arsenide, indium phosphide, or reduced mobility degradation factors using reduced transverse fields. We can also try to reduce the Coulomb scattering due to dopants. We can also reduce the phonon scattering. Okay, so these are the different things by which we can achieve or we can affect or tune these different parameters. Which another is here ensuring device stability to a shorter channel length. So we can use generalized scaling factor lambda scaling rule or channel length LGU. So this maintaining good electrostatic control of channel potential, we can achieve this here. Uh, so we can use to achieve this double gate ground plane FETs, ultra thin body SOI. In this, we can control the device physical geometry and provide means to terminate drain electric field so that short channel effects are reduced here. We can also use sharp doping profiles like for halo doping or pocket implants. Okay, so these are different things which we can do to achieve such goals here. Parasitic resistance. Okay, so we can also try to reduce this parasitic resistance here. So this can be done by using extended or raised source drain. So if we to reduce the resistance, we can make a bigger source or drain, and to make it bigger, we can extend it or we can uh, raise the source and drain. So that already we have discussed. Parasitic capacitance is another thing. We need to reduce the parasitic capacitance to achieve a higher performance goals of the devices. So different parameters on which we can work are junction capacitances, the capacitance between gate and drain, gate and source, gate and substrate. So these are the different capacitances which we can target. So these can be achieved, these goals can be achieved by using SOI or double gate FETs. So there are different improvements which are possible, and there are different suggested methods also we can see here. So there are multiple ways which can be used here. Okay. So we can actually go and look for ideal MOSFET structure. Which MOSFET structure is ideal or good for uh, better performance, better performance in terms of say scaling, in terms of leakage current, low leakage current, high on current. So all these good qualities should be there, and uh, it should not have any drawbacks. Okay, that is ideal. So different options we can explore like ultra-thin body, band engineered transistors, vertical transistors, FinFETs, double gate transistors. So all different structures we can explore here. And nowadays people have been exploring the nanowires or the gate all around transistors. So gate all around transistors have the advantage that the channel is being controlled all around from all around. Okay, so whereas in double gate transistor, it is being controlled from two sides only. So the fabrication issues are there, but that are being overcome due to the uh, advancement in the manufacturing. So we can have FinFETs. FinFETs can control the channel from three sides. Okay, from two sides, lateral sides, and one from the top side. So FinFET is very unique, is having very unique shape in which the channel comes out of the plane. Okay, so this is non-planar. So just like here in this diagram, we can see 400 nanometer buried oxide, and the top of that the channel is coming out like the fin of a uh, fish. Okay, so because of that, it has got its name. So from the two sides, we can see in this uh, this is being controlled. So actually, FinFET is being used at double gate transistor over here, but we can also place a third gate from the top side, and it can be controlled from the three sides also. So a channel is being controlled from two sides here, which can give more on current, and we can now have several such fins connected like pin 1, 2, 3, and these are also being controlled from both sides, and all are connected say by a source and drain on the other side. Okay, so we may have a multiple fin structure kind of thing also to increase the on current. Some more comments about the FinFETs here. The effective channel width is high here. Here in this here this FinFET is actually being controlled from the three sides. So that's why the effective bits has been increased here, and so the current also increased. On current also increases. So here one can do the threshold engineering also. One can also try to reduce the channel resistance in this. Source drain resistance also one can reduce, as we have seen different things can be done in this FinFET also to further improve this the characteristics of this transistor. A typical FinFET manufactured fabricated at IBM is shown over here. The multiple silicon legs can be seen forming the source and drain sides, and gate is there. So here we have multiple fingers kind of thing here, and that is multiple channels. Uh, we can actually analyze the characteristic of these devices without really uh, manufacturing them and predict their behavior with something called as modeling. Okay, so one can do the modeling of these transistors and predict its behavior. Uh, Also, one can do okay. So FinFET is here. So in this we can do some more uh, channel engineering or source drain engineering, like one is using Gaussian source drain profiles and uniformly dot channel region. Okay, so different things can be done to improve the characteristics of these transistors further. A comparison of the double gate FinFET and triple gate FinFET is shown over here. So in the double gate, we can see the isolation for the third gate from the top side. It is more, whereas when we want to control the channel from the third side, also with the third gate side here, then we have to keep the isolation to be small. That is the that isolation is going to work like a gate oxide into that. Okay, so effective uh, bits we can see here on the transistors. So triple gate devices show 20% almost greater drive current than the double gate for the same size. So drive current, as already we have seen, is increased. But in FinFETs, because of the corner regions as shown over here, there is some corner effect. So these corner regions, they are actually being controlled from two sides. Okay, from one this side and from one other side here. So that's why it is difficult to switch off these corner regions easily, and as uh, leakage current may keep on flowing into that, even though we reduce the applied gate voltage. So the corner effects, but these corner effects are not there when we make the channel circular. Okay, so there is no corner in the circular aperture, circular structure. Okay, so corner effect can be removed in a transistor which is uh, uh, circular in nature. So that is being exploited in the gate all around structures nowadays. So different considerations are shown over here in FinFET design. Display length we can select pin pitch, pin height. Okay, so different pins we can use. What should be the minimum separation between these two pins sitting together? So these are the different other issues which can be also looked at. But the ultimate thing is that we can use the FinFET to increase the on current. This also increases layout efficiency. Layout efficiency means we can pack more and more transistors in a given area, because our channel is now vertical. It is now not lateral, it is vertical. Okay, so it is occupying less area. So in the same uh, silicon area, we can put more and more transistors. There are some circuit perceptions also which can be used to improve the circuit performance. So this is actually giving a design flow for FinFET. Okay, how one can use the FinFETs to design the circuits here. So one can do, say, first this device formation here, and do the schematics of this. One can characterize the FinFET using something called as spice models. Okay, so spice equivalent models one can generate for the this transistor, and use this spice model to simulate to predict the behavior of a designed circuitry. So we can typical circuits can be like this fan out of four NAND gates, simple. Okay, so some simple gates can be or simple circuits can be first formed and then benchmarked these spice softwares, and then spice these spice models, and then those can be used for further implementation of the circuitry. Okay, so once we have the device, say it is giving a better performance, we will be tempted to use these devices into circuit. For that, these are the processes which we can follow here. So, so multi-gate replacement. Okay, using these multi-gate transistors, we can use actually we can implement a more complex logic using a single transistor, like in double gate. The double gate transistor is having two gates. Okay. So suppose we are implementing a logic here using two transistors in simple MOSFET. Say this is say two transistors are connected in parallel, so it is most likely implementing the OR gate kind of thing. Okay. So either A or B is on, then we will have some output here. So in actually CMOS technology, we generally are able to implement the negated R, that is NOR gate, okay, because of the few regions, okay, which one can look at. So a double gate transistor in which the gates are controlled independently can be used to realize this NOR gate by using a single double gate transistor. So in that way, we can have a compact circuitry. Okay. So these things we can do here. Here, different options for contacting FinFETs are shown, that how we can in a circuit, just like in MOSFET, we connected the source, drain, and gate regions which were all in the same plane. But because FinFETs are non-planar, so it is difficulty in contacting the FinFETs. But there are different options by using which one can do the which can make the contacts of the source, drain, and gate regions. So end-to-end contact can be made, top contacts can be made, or wrapped contacts can also be made here like this. So these are having say different characteristics as shown in the right side figure here. Okay, so the wrapped contact gives the better uh, one can say properties as compared to the either top contact or end-to-end contact. So top contact is giving the least performance, as we can see, whereas this wrapped contact, this is giving the better performance. So it may be preferred here, but it has some disadvantages also. So parasitics is another thing which can increase significantly. So one can do some layout, proper layouting of these to reduce these parasitics. So just like here, we layout for conventional contact process is shown, which has more parasitics as compared to the right side. So in this way, the layouts can be done to reduce the parasitics. So FinFET can also be scaled here, and because FinFET is now a more complex structure, so we can also see some different things, some which comes into picture when we do FinFET scaling. Like we also have to keep that the source drain resistance should not increase, gate resistance should not also increase that much, because we are having more gates now into this, and integration of these with high K should not be affected much. So these are the things which has to be taken into account, and for these there are different options. Already we have some of these just narrated, and some more which can be also explored. So surrounding gate, high K dielectric material, metal gate, Schottky barrier, strain channel, MOSFET. So these are the different, one can say, evolutions of the MOSFET that we can see. Out of these, which has to be used and which not to be used, that one has to decide. Here we have the ideal MOS transistor, which is all around, and source and drains we can see these can also be fully wrapped to have a better on current here. The channel is also wrapped from all around, so this is going to give a better control over the channel. We can Okay, so such a structure seems to be ideal for the transistor, and this is the structure which is being widely being explored here. So we can do here. We can use high K gate insulator to further enhance the characteristics here. We can also uh, we can also have low resistance source drain by doing some engineering in the source and drain here, and also we can do some in the channel engineering. Okay, we can do something called as band engineering in the semiconductor to enhance these different qualities of the semiconductor, like mobility, etc. Okay, so that will further enhance the ion current. So the different options are even now open here to explore the source drain materials, to explore the depth materials, to explore the gate materials, to explore the metal gate. But this seems to be ideal structure for the MOS transistors, which has evolved throughout several decades. Apart from the classical transistor operation, we can also go for some novel device operation, which are in the classical operation. What we have seen that the some of the carriers coming from the source go into the channel, and they are being collected by the this drain. Okay, they go on the drain side. So there is something called as barrier on the between the source and channel, which is being controlled by the gate. So we have the gate which controls this flow of the charge carriers between source and drain. So that is the classical mass transistor. And there are some novel operations like it is entirely different phenomena by which the carriers are going to flow between source and drain of such a transistor. So this is called as tunneling effect. So we can use the tunneling effect to make something called as Saki tunnel activities. We can have the resonant tunnel devices. We can also have Schottky barrier MOSFETs. If the channel size is so small that the carriers leaving the source reach the drain side without any collision, then such a device is called a ballistic transistor. So ballistic transport okay comes into picture in such a device. So these are entirely new way of operating these devices as opposed to the MOSFETs. In the MOSFET, we have a barrier, actually, potential barrier kind of thing, which we can lower or make it down depending on the applied gate voltage. And also, we can induce the channel by applying gates suitable gate voltage, and then by applying a drain to source voltage, we make the current to flow between the drain and source. So we can have the different fit, okay, MOSFETs here, okay, which we call as now tunnel FETs. These actually have different operation. So tunneling effect happens. Tunneling effect means if there is a barrier, even though we don't need the carrier to overcome the barrier, but it can penetrate through the barrier and appear on the other side. So that is what the tunneling effect we mean here. And based on this, we have these tunneling FETs also. So for this, we have to make the fulfill some conditions for which the tunneling may happen. So such a interface has to be made between the source and channel. So some other alternative device structures can also be are possible. Really don't resemble with the normal working of the MOSFETs. Okay. So like here we have uh, it doesn't look like this regular MOSFET here. Drain is here, and source is here, and controlling gate is somewhere here. Okay. So these kind of different structures can be also explored, but these do not work based on the MOSFET concept. These work on the tunneling concept. We can also do, I think we have discussed MOSFET and engineering. We can do something called as super steep retrograde bells. We can make. We can do halo implants. We can do lateral asymmetric channel we can make it. Okay, so these things can also be done in a MOSFET to further improve the uh, performance of the MOS transistor. So, few are the criteria, design criteria for channel engineering. Like we want to maximize the device drive current, minimize the device short-term effect, and maximize the device pull-through resistance. A lateral asymmetric channel MOSFET fabrication process is just given over here, which has been developed jointly with Ukla and IIT Bombay. So we are approaching actually to a red brick wall. After this red brick wall, we uh, actually this is old data, so it is placed somewhere. One can say 2000 between 2005 and 2008. But still, this red brick wall can be seen to appear. Before this, we know, but after this, what is going to happen, or we don't really know much about that. Like contamination control, P oxide, the red values. Okay, these are alarming here. Junction depth, metal cladding, intermetal dielectric. Okay, so we don't see any much improvement in these. That's what this is. That's why it is called as red brick wall. So after this, things are not much clear. What is going to come next? So these are the different technology challenges which one has to tackle here to overcome this red brick wall. Okay. So challenges are the equivalent oxide thickness, the microprocessor contamination control, the gate length, the accuracy, the wiring, all these things one has to tackle to see. There are some potential solutions for these on the lithographic front. That is, in the lithography also, we can see that there has been a big lapse here. In we have been using for since long here the 180 nanometer krypton fluoride lasers, okay, for photolithography, which led to breakthrough in 2002 by using 130 nanometer wavelength, and then later it was replaced by 100 nanometer, then 70 nanometer, 50 nanometer, 35 nanometer. Now, even now, we are working with this extremely ultraviolet wavelength for photolithography. So, uh, we have been able to give this possible solution on the lithography front, and this is what is making possible the fabrication of such small size devices. So even now we are using this extremely ultraviolet uh, rays for photolithography. So let us summarize here the MOSFET scaling scenario here. The MOSFET size has been continuously reduced from a very big size of a micrometer size to sub nanometer size, and we have started with classical MOSFET and went for ultra thin body SOI MOSFETs. Then we him for multi-gate transistors. And next, it is being explored the strand silicon transistors to further improve the behavior of the MOS transistors. The road beyond bulk CMOS. So we can see here that almost we are at the end of this road on which we have been traveling so far since last I think 6 to 7 decades using the CMOS, but it is no more uh, possible to further scale down the size of the transistors below say say already 3 nanometer. When we are talking, probably we have to stop here 2 nanometer or 1 nanometer so because of the physical limits we are achieving. So different other transistors like a single electron transistors, nanotubes, molecular devices, RTD, resonant tunneling, FETs. So such devices are quantum dots. These may replace these conventional CMOS transistors in near future, but of course we cannot deny the role of our CMOS transistors. CMOS transistors are being widely used to fabricate, to manufacture in bulk. Okay, the today's circuits. Already in the starting slide, we have seen that a larger portion of the digital circuit design and analog circuit design, these are being catered by the CMOS transistors. So we cannot deny here the CMOS transistors. They will be used for coming few decades maybe, and after the mature of the fabrications and technology of these different other substitutes which are being actually uh, being aggressively thought of, they may come in near future. With this, we shall stop here. Thank you all. If you have any questions, we can interact.
Okay. Okay, dear participants, if you have any queries, please unmute your mic and feel free to ask the queries. Do you have any queries? Okay, no. If you have any query, then please message us in chat box. If the sir is here, then we will convey him your queries. Okay. Now, very good afternoon to everyone present here. On behalf of Electronics Engineering Department of IERT Prayagraj, I, Jitan Kumar Shukla, deem it a great honor and privilege to summarize this session and to propose a vote of thanks for such an inspiring session. I use the word inspiring for this session because the way Professor Santosh sir explained, share his knowledge and research findings makes this session truly inspirational and fruitful for us, not only from academic point of view, but also from research point of view. So first and foremost, B Electronics Engineering Department of IERT would like to express our heartfelt thanks to Professor Santosh Kumar Gupta sir uh, from Department of Electronics and Communication Engineering, Motilal Nehru National Institute of Technology, Prayagraj, for sparing his valuable time for this session. The lecture delivered by Professor Santosh sir in this session was extremely informative and inspiring one. He explains several concepts and research findings with us. He started his talk by explaining the various factors that affect the performance of any circuit or devices, such as complexity, delay, power consumptions, cost issues. He also highlights on the importance of design time and size of the devices for designing the high performance circuits and chips in such a rapid changing technology era. He also explains the areas where we can work as a researcher in micro and nano electronic devices. He explained the various basic concepts such as MOS capacitors, MOS transistors, sub-threshold characteristics of MOS transistors, and he highlighted the importance of scalings and different type of scaling and its effect on performance of device and its limitations also. In this lecture, he explained the different technology node and lower technologies, their limitations, transistors integration capacities, challenges for CMOS scaling, and he also explained or discussed the remedies for problems that come during the modeling of good semiconductor devices. During this lecture, he explained the issues of sub-threshold leakage, gate leakage problems in detail, and also explain about the power crisis and power extrapolation curve. He also explained the AMD technology development and power challenges and solution technologies such as FEOL, BEOL, and importance of interconnect in technologies for different technologies node. He also explained the different noble structure for reducing the leakage and power. At last, he explained the various FinFET structures and its important application. Along with it, he also explained the MOSFET channel engineering. And at last, he explained where the technology is approaching, that is red brick wall concept. As a participants and as an organizing team, sir, we do not have enough words to express our gratefulness to you for accepting our invitation and delivering such an enlightening session. Thank you, sir. I am also thankful to Dr. Yatendra Gaurav, sir, coordinator of this ATAL FDP, for giving me the opportunity to propose a vote of thanks for this session. We, Electronics Engineering Department of IERT, remain thankful to the all participants who joined this session to make it successful. I hope you all are benefited from this session. Once again, thank you all for your attention. Thank you. Thank you, sir.
Thank you all very much.